Hello, everybody. Thanks for joining us. This time we have Andrew Svesko from Arizona State University, who is going to tell us about gravity from entanglement and thermodynamics of stretched light cones. So please, Andrew, take it away.
All right. Yes, thank you. Thank you for the invitation and the opportunity to talk about my research, and all of you who are participating in this virtual seminar. This is the first time for me. So today I'm going to talk to you about some work my advisor, Malik Parikh, and myself put out back over a year ago now, related to space-time thermodynamics. And also I'm going to talk to you about a solo project I put out not too long ago, close to a year ago now, related to also space-time thermodynamics, but including some flavors of space-time entanglement. Okay. So in the early 70s, Bekenstein and Hawking showed that black holes have an entropy, a thermodynamic entropy, proportional to the area of their event horizon. And if you look at their expression, the Bekenstein-Hawking formula, you'll find from the collection of constants we often neglect to write that black holes lie at the intersection of quantum mechanics, gravity, and thermodynamics. And what's more is black holes aren't the only spacetimes that carry an entropy. For example, you can look at the cosmological horizons in de Sitter space. They also carry a Bekenstein-Hawking entropy. Or you can study Rindler spacetime with their observer-dependent Rindler horizons, which also carry a temperature proportional to their acceleration, and they also have an entropy. So collectively, this suggests that space-time itself encodes information about thermodynamics and quantum mechanics. And about 2 decades after Bekenstein and Hawking's famous formula, Ted Jacobson showed something even more remarkable. He showed that if you zoom in on local patches of spacetime, and you apply to these local patches a set of thermodynamics, such as a temperature and an entropy, then you can show that ordinary or elementary statements in thermodynamics, such as the Clausius relation, gives rise to the Einstein equations. And so this tells us that Einstein gravity, in particular, emerges from the thermodynamics of spacetime. And how Jacobson's argument actually works is that you take an arbitrary point in an arbitrary spacetime, you zoom in about this point, and about this point you can look at local flat enough regions that you can define a space-like foliation. And on these local patches, you can assign a set of Rindler coordinates with their very own Rindler horizons, characterized by Cartesian boost vectors, which describe the trajectories of some set of so-called local Rindler observers. And then if you apply or assume that these local patches carry a set of thermodynamics, namely an entropy and a temperature, where the temperature is proportional to these local Rindler accelerations, you can show that by applying the Clausius relation about each point in the spacetime, that Einstein's equations necessarily are satisfied about each point in the spacetime. Now, if you study Jacobson's method using the local Rindler horizons, was that a question? Yeah, okay. So if you study Jacobson's method using these local Rindler horizons, and there's a couple other techniques he uses, you realize that he cannot actually account for higher derivative theories of gravity. So the natural question is, can one derive the equations of motion for some higher derivative theory of gravity using a similar setup, or is general relativity unique in this way? And another question that comes up is, what are the microscopic degrees of freedom that are encoded in space-time thermodynamics? And so what I'm going to tell you today is that if we use a different geometric setup, we can actually answer the first of these questions. And this is based on the work my advisor and I, Malik Parikh, put out. And then also I'm going to provide some clues in answering the second of these questions, which is based on the solo project I put out close to a year ago.
So, sorry,
yeah.
I do have a question.
Yeah.
Are the equations that you get from this procedure by Jacobson the full Einstein's equations, or a linearized version of the?
Yeah, they're the full nonlinear Einstein equations.
Okay.
Correct. Yeah, and that's an important it's an important calculation that's people are trying to work out in the literature and other using ADS-CFT and so forth. But I'll get to that later.
Okay.
And so essentially, for a roadmap for this talk, is I'm going to split up into 2 halves. I'm going to first describe the derivation of Einstein's equations in particular, using a Clausius relation, and then relate that to higher derivative equations using some thermodynamics. And then also, I'm going to, in the latter half of the talk, I'm going to talk about deriving Einstein's equations and understanding the underlying microscopics using entanglement equilibrium, which is another one of Jacobson's proposals. Okay. So our derivation of the Einstein equations using the Clausius relation is going to follow a very similar spirit to Jacobson's original derivation. So what we're going to do is we're going to zoom in on an arbitrary point in an arbitrary spacetime. Locally about this point, we can define a space-like foliation with respect to some time coordinate we'll label t. And then emanating from this point P is a light cone. And now the surface we're going to be interested in is a congruence of radial boost vectors. And the surface that this sweeps out is some time-like stretched horizon of the light cone. So it's a time-like surface, and it actually forms the stretched horizon of the future of the light cone, I should say. We're going to denote this surface using capital sigma. And it's important to note that cross-sections of this surface are codimension 2 spheres. Okay. Now, crucial to our derivation, as well as Jacobson's, is the fact that we're using that locally any spacetime looks flat. And one way of quantifying this is that we can take an arbitrary metric of an arbitrary spacetime, and we can decompose it using the Riemann coordinate expansion, which basically says any metric can be written as Minkowski space plus some curvature contribution evaluated at that point P. And what happens with this is that vectors that might have been killing in Minkowski space, such as the Cartesian boost vectors, they become what's known as approximately killing vectors. So what we mean by that is that Killing's equation and Killing's identity are no longer satisfied, but rather they only hold to some order in the Riemann coordinate expansion. Okay. And now our radial boost vector, we should say we're going to call it an approximate killing vector. However, we should note that it's not even a killing vector in flat space. And this is because it's not, radial boosts are not an isometry of Minkowski space. Nonetheless, we're going to keep calling our radial boost vector an approximate killing vector because it does satisfy Killing's equation up to some order Riemann coordinate expansion to some degree. And so it effectively acts like a approximate killing vector. Might be an abuse of language, but we'll call it nonetheless. But this will be an important feature that we have to keep track of as we proceed with the derivation. Okay. Now, even though a radial boost vector is not exactly killing in pure flat space, in pure flat space, the radial boost vector describes the trajectory of a constantly radially accelerating observer. So this tells us that the stretched future light cone actually represents a time-like congruence of constantly and uniformly radially accelerating observers with some acceleration a. And this construction actually holds in, or description, holds in both flat space and curved space. So it takes a little extra work to show how it holds in curved space. Okay, so that tells us that our stretched future light cone is in fact a surface of constant temperature if we allow ourselves to assign a temperature to this set of radially accelerating observers. And in fact, the temperature is just proportional to the acceleration of these observers, which we can understand as a spherical Rindler horizon. Okay, and so since it's a surface of constant temperature, that tells us we are dealing with a thermodynamic system that's in equilibrium. Now, since we have assigned a temperature to our system, we're then inclined to assign an entropy to our system. And so we're going to make the assumption that we can assign an entropy, a thermodynamic entropy, to the cross-sectional area of our stretched horizon. So this is an assumption we're going to make, that we can assign an entropy and that we can assign the entropy such that it satisfies an area law. And in fact, this is motivated and consistent with the black hole membrane paradigm, where we can assign entropy to cross-sections of the stretched horizons of black holes. And just because it'll be useful later on, we can actually write the cross-sectional area A at some time t in terms of the proper velocity and the normal vector to our radial observers. And then if we define a binormal area element of our codimensional 2 spheres, we can write the Bekenstein-Hawking entropy at some particular time slice in the following way. Don't worry, you won't have to memorize this. This will just be useful for us moving forward. Okay, so now we have all the elements necessary to derive Einstein's equations. So there's basically only 3 elements to the proof. First, we're going to determine the change in entropy using a physical process. And so what we mean by that is we're going to drop in some matter past the horizon of these spherical Rindler observers. And then we're going to simply take the difference between the areas at some time t equals 0 and some later time t equal epsilon, and compare or compute the area difference, which will then give us the change in entropy. Then we're going to define what we mean by Q, heat. And finally, we're going to apply the Clausius relation and look for what the geometric consequences are. Okay. So step 1, we imagine depositing some matter past the stretched horizon of this future light cone, which we denote here by Q. And then we're simply going to compare the change in area due to this falling matter at the time t equals epsilon and t equals 0. And so that simply means we're just going to take the area difference between these two. And when we do this is we use what we wrote before with the Bekenstein-Hawking entropy and that integral formula, compute the difference. And since we're on this closed surface, we can apply Stokes' theorem, and we can write the total change in entropy over our stretched light cone, sigma, in the ways you see here. And if you look at this particular term up here, it's begging us to use Killing's identity. However, we have to be careful because our C is not an exact Killing vector. So to quantify this fact, we include an additional term, FBCD, which denotes that C is not an exact Killing vector. However, just because this term is annoying, and because we might not know how to deal with it just yet, let's just see how the rest of the proof carries through, and let's drop this term for now. We'll come back to it, but let's just drop it for now. So dropping this additional piece F and plugging in the Killing's identity, we use these various contractions G on the Riemann tensor, and we can show that we can write that T delta S is equal to this geometric expression here in with respect to the Ricci tensor at some particular point P. Okay. Now, step 2. So now we need to know what we mean by heat. Well, the way we do this is we recall our basic elementary courses in thermodynamics, where one way of understanding heat is that it is the energy that flows into macroscopically unobservable degrees of freedom. So that's not the original way I learned it, but this is one way of actually understanding what we mean by heat. And if you look at the stretched light cone, the interior and the exterior of the light cone are out of causal contact with one another. And so this means that the interior is unobservable to our Rindler observers existing on this outside time-light congruence. So in that sense, the integrated energy flux incoming into the stretched light cone would be interpreted or measured by these Rindler observers as heat. So we're going to identify this integrated heat or energy flux as a heat flow. And now we can just put everything together and apply the Clausius relation. So by applying the Clausius relation, you can set the two integrals together, and with a little bit of work, you can set the two integrands together. And finally, after some further finagling, we arrive to our prize, the Einstein equations. And so this tells us that Einstein gravity emerges from the thermodynamics of stretched light cones about each point in space-time.
Sorry, how general is that statement? So were there some underlying assumptions, or?
So the only assumptions that really go into this, and I guess broadly this is called thermodynamical gravity, is that first that we can zoom in on arbitrary patches, but that's, we can always do that with a spacetime. The first real assumption is that we can assign thermodynamics to these local patches, and that so that includes a temperature and an entropy, but we have to have motivation for each. So the motivation of temperature, I think, is somewhat well motivated because we can always describe either a set of local Rindler horizons, as Jacobson did, or in our case, we kind of have a set of local spherical Rindler horizons. And you can always assign the temperature to the acceleration of these observers. Now, when it comes to the entropy, that's a much larger assumption. We're going to assume that the entropy goes like the area. So this is an assumption about the thermodynamics, but it's motivated from black hole physics, as well as studying the thermodynamics of other types of spacetimes. So it's an assumption, but we're also assuming the form of the entropy as well, that it goes like an area. But as you'll see later, we'll relax one of those assumptions or modify one of the assumptions, and that will be the key in how we get higher derivative equations. But other than that, those are the only assumptions we really have to input into this derivation.
And that f that appears in the equations here has nothing to do with the f that measures the fact that the killing vectors are not really killing vectors?
Right. I probably should have called this phi or some scalar function.
Okay.
And all it does, so all it happens is when you set the integrands equal to one another, you find this top expression here. And then we're going to use the fact that n and c are orthogonal to one another. And so we can rewrite this statement here as the following statement in the middle, where now we've just included a term that quantifies the fact that we use this orthogonality condition. So we can have something proportional to the metric, and it's some scalar field. And then if we then demand that the energy momentum tensor is conserved, so we apply nabla to both sides, then we can find that f is fixed to be r/2 and actually plus some constant, which we interpret as the cosmological constant. Yeah. Okay. Now, to get to this point in this derivation, we had to neglect the fact that C was not exactly killing. But the point is, we saw before that C is not a killing vector, and it's not killing for two reasons. First, in ordinary flat space, it's not killing because radial boosts are not isometries in Minkowski space. And second, because we're working in a curved background, there's going to be some corrections due to the curvature expansion and the Riemann-Euler coordinate expansion. And this will lead to terms like this in the change in entropy, where now we include this FBCD. And so if we want our proof to go through, seemingly we have to argue away, or reasonably argue away, the effects of this contribution here. Okay. Now the way we deal with that is there are two ways. First, we're going to modify C in such a way that we add higher order corrections to it, and we can add these corrections in whatever way we want, so as we can eliminate the higher curvature contributions coming into FBCD. And we're going to add these higher corrections in such a way that it doesn't change anything we did before when we defined our stretched light cone. And this can be done. It takes a lot of work, like about 20 pages of an appendix of work. And you can show that just by modifying C and using a couple other tricks up our sleeve, which are just purely mathematical, you can eliminate all the contributions to FBCD coming from the Riemann-Euler coordinate expansion, leaving only a single quantity in FBCD, which is coming from the fact that C is not a killing vector in flat space. So now we have to deal with that. And to do that, let's recall what we're actually doing in this setup. What we're doing is we're considering a physical process where we drop in some matter and we're measuring the change in entropy due to this falling matter. However, the light cone is going to expand naturally, irregardless if there's matter. So if you actually go through and you set the energy momentum tensor for that matter contribution, if you set it to 0, you'll find that there's still a positive change in area, and therefore a positive change in entropy. And in fact, if you go through and calculate, you can show that that single term appearing in FBCD is precisely measuring that natural expansion of the future light cone. So we're not interested in that term. And also it represents some irreversible thermodynamic contribution. What we're interested in is just the contribution to the change in entropy due to some falling matter, which we interpret as some reversible entropy, or some reversible thermodynamic process. And so we simply subtract off this extra term coming from the natural expansion, and we define the reversible entropy change. And in fact, this is the term, the reversible entropy change is what appears in the Clausius relation anyway. So then the rest of the proof goes through. All we have to do is go back and edit what we had written before, where we replace delta S with our reversible entropy change, and voila, we arrive to the Einstein equations. And this time using the Clausius relation in perhaps a slightly more proper form. Okay. Now, at the beginning, I advertised that we could use this geometric setup to answer the question whether or not we could derive equations of motion for more general theories of gravity. And the answer is yes. So what we have to do is we have to modify one of our assumptions early on, which was the form of the entropy. So rather than assigning the entropy to cross-sections of the area, what we're going to do is we're going to change that area law, and we're going to replace and assume that the entropy ascribed to the cross-sections of our surface goes like the Wald entropy, which I'm sure many of you know is the no other charge of the with respect to the diffeomorphism invariance of some higher derivative theory of gravity that's living in our system. So again, we're not assuming that we have this higher derivative theory of gravity, and this is an assumption about what the form of entropy takes. But when we do assume this, suppose this is some God-given assumption, that then we can go through the rest of the derivation and just the same, and we compute, we define Q in the same way, and we compute the Clausius relation, this time replacing the Bekenstein-Hawking entropy with this Wald entropy functional, and we arrive to the equations of motion for higher derivative theory of gravity. And so more specifically, the kind of theories of gravity this includes F of R gravity, Einstein gravity, of course, but also things like Gauss-Bonnet gravity. The form of this theories of gravity that this can include is anything where the Lagrangian depends on the metric and the Riemann tensor, which is pretty general. So the only thing we didn't include here is our theories of gravity that include derivatives of the Riemann tensor, though we expect the derivation to go through in a similar way. So this shows that any theory of gravity emerges from the thermodynamics of space-time. So to briefly summarize what we've shown so far, we showed that we can actually assign thermodynamics to time-like surfaces. We can give an entropy and a temperature to this time-like stretched horizon of a future light cone. We then showed that we can use Clausius relation to derive the equations of motion for any theory of gravity. And in particular, in our derivation, we separated out the reversible and irreversible contributions to the thermodynamic process. And though I didn't show it here, one thing you can do, if you allow me to toot our own horn a little bit, is there's another paper that my advisor and I wrote together with a collaborator of ours, Sujipi Sarkar, where if we use the results of this Clausius relation giving rise to equations of motion, you can apply that and actually derive what we've been calling a local first law of gravity, which is reminiscent of the first law of thermodynamics of black holes, except that this statement holds at each point in an arbitrary spacetime, and it includes a pressure term that is often lacking in the ordinary laws of thermodynamics for black holes. And you can find that paper here. And perhaps most important, we have reaffirmed that classical gravity is the thermodynamic limit of some underlying microscopic theory of spacetime. Okay.
So, yeah, a short question: does it depend in any way on the process you use itself? So, that generates heat. Do you need? Do you have any assumption on that, or?
Any assumption on what specifically?
On the process that generates the.
So yeah, I guess there are some somewhat hidden assumptions that we're assuming that. So for example, we don't assume anything about the form of matter. We can just drop it in. And I guess what we're assuming is that when we're comparing the two time slices, we're assuming that the time that this takes, the time epsilon, we're assuming that that time is much longer than the time for the system to equilibrate. So we always want to make sure we're using equilibrium thermodynamics here. And so we compare the two the two areas at different times, but it's not so much longer that the temperature is different, but long enough that we have, that we're still, or that the system is equilibrated after we've dropped in the matter. But the actual form of the matter itself, it doesn't matter what it takes. There's no assumptions on that, at least.
And this also holds in any space-time dimension, in principle.
Correct. Yeah, it holds in any space-time dimension. The only thing about the space-time that I think you have to be careful, which I think is perhaps assumed, is that we're saying this applies to any point in space-time. However, we're imagining that we can apply this at particular points in space-time. So we cannot, say, look at a singular point in a space-time and apply the same technique, because we want the Einstein equations to hold at every point in space-time. So I think if we were to try to adapt this and say, can we apply this at singular points in a space-time, the answer would be no. Yeah. Okay. So the remaining question is, what are the microscopic degrees of freedom that's encoded in space-time thermodynamics? And for the rest of this talk, hopefully I can provide some clues to this. So to answer this question, let's actually take a step back and ask the very same question about black holes. What is black hole entropy? And so let's consider a quantum field theory in some arbitrary space-time, and let's compute the entanglement entropy due to vacuum fluctuations on either side of a boundary. And we can take, for now, we'll take this boundary to be that of an event horizon of a black hole, which is perhaps the most natural setting to consider entanglement entropy across boundaries. And you'll find that the entanglement entropy is UV divergent. So you introduce UV cutoff, epsilon here, and you'll find the leading UV divergence to the entanglement entropy satisfies an area law, where the area is now the area of the boundary that's, or the boundary encoding some particular region. So if we then compare this to black hole physics, which also satisfies an area law, it's very enticing for us to then set these two equal to one another. In fact, we set the two coefficients to one another, and then interpret the Bekenstein-Hawking entropy as the entanglement entropy between vacuum fluctuations inside and outside of the horizon, or at the very least, the leading UV divergence. So the question is, how can we set these two equal to one another? What's the motivation? And also, that leads to the question of how does classical gravity know about the entanglement entropy? And the short answer is that classical gravity, one answer in this, is that classical gravity can be understood as arising from an induced action representing one loop quantum field theory on some arbitrary background. And the quantum fluctuations that give rise to the entanglement entropy are precisely the same quantum fluctuations that give rise to this to Einstein gravity, including its gravitational coupling G. So more specifically, if you look back to Sakharov, he showed that if you study one loop quantum field theory on an arbitrary curved background, that you can compute the one loop effective action of these classical fields, or of these quantum fields on this classical background, and you find that a contribution to this effective action includes terms like the Einstein-Hilbert action, as well as some higher curvature expressions as well, and that the gravitational couplings of these curvature contributions, including Newton's constant, are renormalized by the matter loop divergences. And then, if we then compute the entanglement entropy of a quantum state living outside the horizon of a black hole, then you can show that the leading order contribution to the entanglement entropy is precisely given by the Bekenstein-Hawking entropy, where now we've written the Newton's gravitational constant as this renormalized contribution from the matter loop divergences. And so that tells us why or how classical gravity knows about this entanglement entropy. Okay. So not only does this tell us that the Bekenstein-Hawking entropy is the leading divergence, UV divergence of the entanglement entropy, but also the subleading divergences come from these higher curvature contributions to the one loop effective action, and that these gravitational couplings are renormalized in the very same way. And so that tells us the entire UV divergent structure of the entanglement entropy comes about from this induced gravitational action. And so we represent it as the Wald entropy dependent on some UV cutoff. Now, there's an extra term to the entanglement entropy, which is this finite contribution. So the question is, how do we interpret that? Well, if we assume that quantum gravity is UV finite, as people suspect with string theory, then a calculation of entanglement entropy in such a theory should be UV finite as well. And it turns out that you can study the generalized entropy in particular models, and you find that it's independent of this UV cutoff. And so then we're going to make the assumption that the entanglement entropy is identified with the generalized entropy in a full complete UV or a full UV finite theory. And then once we make this assumption, we can identify that finite contribution to the entanglement entropy as the entanglement due to matter, or the entanglement entropy due to this matter contribution. Okay, so that's one of the big assumptions about this particular setup. And now, just as we did with the Bekenstein-Hawking entropy, we can apply the generalized entropy to surfaces other than black hole horizons. So for example, if you apply the generalized entropy to, say, a minimal bulk surface in an ADS space, you'll find that the generalized entropy is actually the quantum-corrected Ryu-Takayanagi formula, which is computing the entanglement entropy of CFTs living on the boundary of this space. Okay. Another example is you can consider causal diamonds living in a maximally symmetric background. And then if you apply a constant volume variation to these causal diamonds, you can show that the vacuum is in fact in a maximal entropy state, where the entropy decreases, the entanglement entropy decreases. And this statement, written by Ted Jacobson back in 2015, is known as the entanglement equilibrium conjecture. What's more is if you then apply the first law of entanglement entropy in conjunction with the entanglement equilibrium statement, you can derive the Einstein field equations about any point in spacetime, the nonlinear Einstein field equations, plus the linearized equations for higher curvature theories. And so this tells us that gravity, in fact, emerges from spacetime entanglement. Okay. So we can ask the very same question about stretched light cones. Can we imply entanglement equilibrium proposal to stretched light cones, and can we likewise derive the equations of motion? And the short answer is yes, we can. And instead of going through all the mathematical details, which there are quite a few showing this, instead I'm going to provide some motivation why we'd expect this to be the case. And then I'll also provide an outline of the proof that explains some of this. Okay, so crucial to Jacobson's derivation is that he's using the fact that the causal diamonds have spherical subregions, and that the causal diamond is generated by a conformal killing vector. Okay, now with our stretched horizon or stretched future light cones, we already saw that the cross sections of this surface are also spherical subregions, and it turns out that the radial boost vector, in some ways, in flat space, acts like a conformal killing vector. So here I've written in red that if you study the Ij components of the Killing's equation, you'll see that the leading contribution here, or this contribution here, looks like that of a conformal killing vector, satisfies the same properties. And in fact, this observation was an offhanded comment by Ted Jacobson when I was visiting with him one time. And this comment is what led me onto to studying this whole problem to begin with. So because of these two elements, that we have spherical subregions, and because the radial boost vector acts in some ways like a conformal killing vector, we can apply much of the same argument that led to Ted Jacobson's entanglement equilibrium and his derivation of equations of motion to the case of stretched light cones. There are some important differences, and you have to keep track of the fact that our vector here is not an exact conformal killing vector, and so you have to be careful. But the point is, most of the important steps that go into the derivation will precisely match on to the stretched light cone. Okay, so now the outline of the proof is that we're going to derive first an off-shell geometric identity, which I've been calling the first law of stretched light cones. There's a lot of first laws here. And the way we're going to do this is we're going to use an equilibrium process. So we imagine some matter perturbation, and then we compare two nearby light cones. Then we're going to apply the first law of entanglement entropy to this matter perturbation. And finally, we're going to impose the entanglement equilibrium conjecture and see what follows. So in step 1, we're going to consider a matter perturbation to a maximally symmetric space. We'll take it to be Minkowski space. So we're perturbing Minkowski space. And the matter piece we're going to write as it's measured with respect to the accelerating observers. And then we're going to compare 2 nearby stretched light cones. Now, when you do this, the mathematical techniques that leads to this boxed equation here are precisely, or very similar at least, to the same manipulations we did to derive the Einstein equations from the Clausius relation. So I won't show them here, but you can actually show the mathematics there equally applies here in this equilibrium process. Now, the right-hand side here, there's a few things to note, is that when this side equals 0, this is an equivalent statement of Einstein equations being satisfied at each point in space-time. So in other words, this delta C represents the gravitational constraints for Einstein's equations being satisfied. Okay. Now, if you look at the left-hand side here, if you look at these 2 terms, these differences in entropy, this is in fact the variation of the entropy fixed at constant volume. And in fact, most remarkable perhaps is that this term precisely gives you the exact same expression we find when we look at the irreversible entropy change, which means this delta S bar in some ways can be interpreted as the removal of that extra piece coming from the stretched light cone naturally expanding. So we're moving this irreversible contribution. And in fact, if you look at this entire left-hand side, this entire left-hand side is essentially the equilibrium process expression of the Clausius derivation of the Einstein equations. So this tells us that there's a deep connection, or an interplay between equilibrium thermodynamics and entanglement equilibrium. And what's more is you can actually derive the same geometric law using the Iyers-Wald formalism, which is usually employed in the literature these days as like an additional mathematical check of this expression. Okay. So now the next step is we're going to apply a simultaneous variation to the entanglement entropy on the stretched light cone with respect to both the geometry and the quantum state. And since we're assuming that the entanglement entropy goes like the generalized entropy, then the change in the geometry, that's going to only provide the constant volume variation to the gravitational piece, which is here represented by the Bekenstein-Hawking formula, the Bekenstein-Hawking entropy. And the perturbation with respect to the quantum state of matter is only encoded in this perturbation to the matter entanglement entropy contribution. And if we represent our quantum state of our matter using this density matrix in terms of a modular Hamiltonian, so we can always do this. Well, in general, the modular Hamiltonian, the form of it is rather obscure. However, when we assume, this is another assumption, that if the matter is conformal, that, with the fact that we're working on spherical subregions, means we can apply the Cassini-Huerta-Myers map. And we can then show or write that the modular Hamiltonian can be understood or rewritten as the spherical Rindler Hamiltonian. So this tells us that the first law of entanglement entropy on this matter contribution here is actually, we can replace it with this contribution here, the variation of the spherical Rindler Hamiltonian, which is representing that matter perturbation. Okay, so if we take this and we apply it to our previous statement about our first law of stretched light cones, combined, we have the constant volume variation of the entanglement entropy is equal to that set of gravitational constraints. Okay, and finally, if we apply the entanglement equilibrium condition, that if we assume that the entanglement entropy is maximal in the vacuum, then that means we're going to set this side equal to 0, which then sets those gravitational constraints equal to 0, and we arrive to the Einstein equations. So this tells us that the Einstein equations arise from entanglement equilibrium, but applied now to stretched light cones. Okay. And so now let me just summarize kind of all of this. So by assuming that the vacuum state is in a maximal entropy state, we find that a constant volume variation of the entanglement entropy gives rise to the Einstein equations. What's more is this derivation actually extends to higher derivative theories. However, you only get the linearized gravitational equations. And I can answer questions about that in a moment. We found that the fixed volume condition is in fact related to this reversible entropy change. And it connects to the Clausius relation to the statement of entanglement equilibrium. And though I didn't show it here, you can actually you can ask the same question for about causal diamonds as we did earlier. That is, can we study the thermodynamics of causal diamonds and likewise apply an entropy and a temperature to causal diamonds and look at the Clausius relation and derive equations? And the answer is yeah, you can. You again find this need for this reversible contribution, where the change in reversible entropy is precisely that of removing the constant volume piece from the causal diamond. And you can again derive the full nonlinear equations of motion for higher derivative theories of gravity. And all in all, what this tells us is it provides a through line between space-time entanglement and space-time thermodynamics. And so some interesting directions forward would be to going beyond spherical subregions. How necessary is that assumption? How necessary was the assumption about conformal matter? Can we drop that, or can we relax that assumption? And also here in the derivation, I only showed perturbations to Minkowski space. However, you could ask, I mean, most of the setup works for maximally symmetric spaces, such as de Sitter space and anti-de Sitter space. So we could ask, okay, what really changes when we turn on a cosmological constant term and study perturbations about that space? And then another question is, where are the nonlinear contributions for higher derivative theories of gravity? And this is one of the questions that got me interested in this project to begin with, because I looked at the thermodynamic structure of the stretched light cones, saw that we could get the full nonlinear equations by modifying this xi piece, or modifying our killing vector. So that led me to think that, oh, maybe this is a technique that we can use to derive the nonlinear contributions to in the entanglement equilibrium story. However, it actually doesn't work for technical reasons. So that didn't quite work. But I have some other ideas of how this might work, and that's the work in progress at the moment. But with that, thank you for your time, and I'll take any further questions. We can talk as long as you want.
Thank you.
Yeah.
So I have a couple of questions. The first one is the simpler one. Basically, you showed with this construction that using this entanglement condition, you can recover the full Einstein equations, right?
Right. Mm-hmm.
But often you hear in the holographic community that entanglement, and more precisely entanglement entropy, is not enough to reconstruct the whole of space-time.
Right. Right. Are you referring to? So I'm thinking of the work by like Ramsdonck and Faulkner, where they had to use this like modified first law.
For example.
Yeah. Okay. Yeah.
How does this setup fit in
right. So that expression actually never comes into play when you want to derive the Einstein equations. And to me, it is somewhat of a mystery why it actually. So why it takes place. I see it when I look at the papers by Ramsdonck and Faulkner. However, for some reason, when you go through when you derive this this first law of like stretched light cones, or the first law of causal diamonds, you don't actually need. It's a complete geometric expression, and then when you imply the entanglement equilibrium, or the first law of entanglement, you don't actually need this extra contribution coming from, if I remember right, they look at excited CFT states or something of that. So they don't actually need it. And I don't know why they don't need it. However, that is my guess is that when it comes to the nonlinear contributions to the higher derivative theories, my guess is that's precisely the form you need. However, I've not actually yet found a way to implement that properly. But my guess is like that's how you would get these higher nonlinear contributions for these other theories. But yeah, again, when it comes to the Einstein case, you just don't need it, it turns out, which is odd to me. Because I imagine like if you decided to look at perturbations to ADS space, that your derivation using entanglement equilibrium should look very similar to what is done by Brahms, Donk, and Faulkner and all those others. And so you might expect there that you need some nonlinear contributions to the Einstein equation coming from the same arguments that Brahms, Donk, and others had applied. But seemingly you don't need them.
And having said that, could you say more about these higher derivative theories and about linearized gravity?
Right. So the higher derivative theories, they simply come from the same. They come from like essentially the same induced effective action. So they'll include things like R squared, Riemann tensor squared, Ricci's squared, and so you go through and you can simply compute the. So let me go back to this statement. So you assume this form here, but now what happens is you're going to assume the variation of entropy here, and now instead of the Bekenstein-Hawking, it's going to be the Wald entropy. And this piece here is actually only out to some particular order in the Riemann coordinate expansion, and the order in the Riemann coordinate expansion is enough to get the nonlinear contributions for the Einstein piece, but it's not enough to get the nonlinear contributions of the higher derivative expressions. So essentially, the way you derive this is you look down, you see what the higher derivative equations of motion are, you perform some Riemann coordinate expansion on that set, and you're able to deduce what the form of these constraints are. And you find that to the order that you're going to in the Riemann coordinate expansion, you can only consistently get the linearized constraints here. And so that suggests then, but you're able to get a consistent expression for the Bekenstein-Hawking, which then applies for the Einstein equations. But that suggests that to get the remaining nonlinear pieces, it must be coming from here, which is why I think that, okay, the only other time this shows up is when you look at the first law of entanglement entropy, and perhaps we should change what this is. We should change this to being that more generalized first law of entanglement entropy. And perhaps there we'll find these extra nonlinear contributions. Okay.
Are there any more questions or questions from people online? Well, if not, then let's thank Andrew again.